All right, good afternoon or good morning, depending where you are, to what is technically, after having two parts of history, our fourth lecture in the basics of macromolecular crystallography. Today, Jim Pflugrath is going to tell us about the diffraction experiment, crystals, beams, images, and reflections, followed by a second lecture by him next week, which will more deal with scaling and statistics. So Jim has a very long history in crystallography, much longer than my own. He has studied at Rice University, then continued to do a postdoc with Robert Huber in Martinsried in Munich in Germany, continued to Cold Spring Harbor Laboratories, where he, I believe in 1988, started a new course on crystallography, which since then has taught hundreds of ambitious young crystallographers how to do everything from crystallization up to structure validation, and is, well, I think by all accounts, one of the best courses you can attend. It's very comprehensive. He then went on to work for the Molecular Structure Corporation, which was acquired I think in '99 by Rigaku and then incorporated into Rigaku later. Either shortly before or after that, Jim published a software called Star Trek, which is part of Rigaku's Crystal Clear and is an integration program. So Jim Pflugrath has written his own integration software, which for me is quite a feat. He has been dealing with images and what I would call methods development almost all of his scientific life, and is really a capacity in this area. And so I'm extremely happy that he volunteered to give us two lectures in this series and introducing us to integration and scaling.
All right, so it must be that I am sharing my screen now, I think. Is that right?
Yes.
Great. So I'm on here. So thank you very much for the introduction. I would say this, that the Cold Spring Harbor course has not only taught young people, but you can be older and still come to the course or be admitted to the course. And I'm proud of all of the help that I've had with the other instructors, Alex McPherson, Gary Gillen, Bill Fury, Paul Adams, Tassos Parakis, just and more recently Janet Newman, and there's just a ton of people that have helped out with that course. There's no way I could do it all on my own. So I have not done crystallography for something like 5 years. I've been retired for a while, and I do still continue on at Cold Spring Harbor, but I am not the contemporary of everybody. The way that I do things is perhaps, and the way I'm going to lecture is a little bit older, but the physics doesn't change. The science doesn't change of how we do this. And so I'm going to now share my desktop and get on with this lecture. I see that see my friends have all signed in here for the lecture and made themselves known. I like that. We're in inside. So the diffraction experiment, crystal beams, images, and reflections. As far as I can tell, everybody should be able to see this. And what we're going to do is go from molecules to models. And to do this, we get our molecules to start with. In the wet lab, we do a prep, or perhaps somebody mails them to us. We grow the crystals of these molecules. We then subject them to an X-ray diffraction experiment where we collect the diffraction images, which we can call the data. And I saw Gianluca Santoni's previous lecture of how this is done. We'll review some of that, but not too much. And from that, we will then process the images into their Bragg spot. So here's the crystals. Here's a small zoom of an image. You can see these Bragg reflections. Some are darker or more intense than some others that are very light. And these spots are indexed by their Miller indices, HKL, and we will get their intensity and their standard uncertainty. let me ask this. Can people see my cursor moving? And is the cursor big? Because I can't tell. And because I'm sharing a full
We can
screen.
see
Yes,
your
it is.
cursor, and it is medium-sized.
Medium size, okay, but it's not small, I'll say that. Okay,
Yes.
good. So once you get this data, then you can go work it up, which will probably be the rest of this course, where you will solve the phase problem, because these only measure the intensities of these Bragg reflections and not their phases. And then you will need to get their phases, and doing that you can calculate the electron density. And I saw the electron density equation in Jean-Luc's talk, and that would give rise to, you can make a display of that electron density, which is this wire mesh, and you can interpret that in terms of the molecules that are there. And this is a molecule of thaumatin. And then you can build in the carbons, which are yellow here, the nitrogens blue, oxygens as red. Here's a water molecule, here's a carbonyl oxygen, and sulfurs. Here's a couple of disulfide bridges. And this is the model that you can then use to develop or test hypotheses and so on. So we're going to talk today about going from images to intensities. And then next week we will talk about scaling and so on. So of course, all of this doesn't work unless you validate the model. So reflections from images. All software programs, once you collect the images like Jean-Luc talked about, will search for spots, they'll find spots, they'll index. And these spots are X, Y on the detector, and the phi value is the rotation of the crystal. And from these, you can get the crystal unit cell and its orientation in space in a preliminary indexing step. Then you can do a refinement of these spots against the properties of the crystal, the properties of the detector, and the properties of the source, so that you can exquisitely, accurately predict where the spots will be in all your images. And if you are doing this from the first two images, you can then compute a strategy as discussed in the previous lecture. And we won't go much into that in this lecture. But once you can predict where all the spots are, you can label every spot with a Miller index, H, K, and L in 3 space, and then integrate it. And we will talk about that. And next time I will talk about scaling. Okay, so for some reading material on scaling and so on, which you can prepare yourself for the next lecture, I've given these 2 references, which are readily accessible. I think both of these are what do you call them, open access. So I know nowadays a lot of people try to do all their learning on their phones. You know, you read everything on your little handy, but in fact, in the old days before the internet, we read papers, and there's more stuff in these papers than even I can put in this lecture. Ultimately, from what we're doing in my lectures, we're going to end up with a so-called Table 1, which is summary of data collection statistics. The Table 1 has various things in it, but generally at a minimum, it will give you the space group of the crystal that you have studied, the unit cell dimensions, the A, B, and C, the 3 cell lengths, the 3 angles. In this case, it's 90, 90, 90. Something about the order of the unit cells in the crystal, and it's called the crystal mosaicity. The resolution range, there's generally 2 columns of numbers here, but sometimes 3. This shows the full resolution range used in the publication, and the resolution range in the outer shell. These are meant to help you understand how good is the data, and we'll go into this in much more detail. But total number of observations or measurements or reflections, the number of unique reflections. So in this case, we have measured things on average about 5 times each, and that's called the average multiplicity or the average redundancy. Or if you read the CCP4 news group, they're saying, of course, in Europe redundancy, or in the UK redundancy means something else, and maybe replications is being used nowadays, or I haven't followed it closely, but maybe there's more terms. In any event, for this given resolution range, you can actually predict all possible reflections. It's simply a geometric problem, and you want to collect as close to 100% as you can get. As you go out to the edges of the diffraction pattern, you will find that, as Gianluca talked about, sometimes you truncate things by the square of the detector or the rectangular face of the detector, whereas this is normally with a circle inscribed in a square in the detector, but you don't always get the maximum resolution or the highest completeness in the outer shells. There are some R-factor emerging statistics that we'll go into next week that must be reported. So the experiment itself, this shows a piece of hardware at Cold Spring Harbor Laboratory here on the right. It shows an X-ray source coming in from the left, a crystal goniometer here below the center, a detector goniometer that moves this particular detector around. There is a detector, there is a cryogenic gas flow coming in here through a cryo system, and of course the crystal in the center. These things were all mentioned in one form or another in the previous lecture. But what I like to do here is to show that you can come in here and with your hands, you can go in and touch everything, even in a hutch. Maybe the beamline scientists don't like you to touch things, but you can go in and you can put your hand on the collimator. You can adjust the beam stop, and at least in the old days, maybe modern synchrotrons, everything is turned into a robot and you don't get to go in there. The detector you can see. The cryo system, you can come in and put your fingers on here. And of course, at some point, you probably had to manipulate this crystal out of a drop of mother liquor and flash cool it, put it into a puck, ship it to the synchrotron, either put it up here by hand or have a robot do it. In any event, that crystal is the center of your experiment. So all of these objects in here, the source, the goniometer, the detector, I guess I should have pointed here, the source, the goniometer, the detector, the crystal have properties that have to be defined to the software that you're using. So here is an actual experiment done in a home lab. It's a different setup than what you saw on the previous slide, but it has still the same objects. There's an X-ray source coming in here, a crystal here, a detector here, and there's actually a video camera pointing up to the crystal that's shown here, and there's a cryogenic gas flow here. What you're going to see when I click the button is that I don't know if you can still hear me, but the goniometer moved to the start, the shutter opened, X-rays are hitting the crystal, exposing the detector. These are the images coming out, and you can see this crystal rotating. This is a fairly large crystal of hen egg white lysozyme. And these are, you're seeing the Bragg spots and so on. This takes took about 26 seconds, and the shutter closed and the experiment is done. We have collected enough data to solve the phase problem. Let me go on. And this shows the images themselves. It's a two-chip, two-segment detector, and this shows the images as they are collected in a higher resolution there. Okay. And as you can see, the spots change from image to image. Some are strong, some are weak, and so on. So that's the experiment that Gianluca described yesterday. So some of the steps here are you're going to pick up a crystal, plunge it into liquid nitrogen, put it on a magnet on a goniometer head. It's going to optically align it. This is normally done at the beam line by just software and robotics. Take a diffraction image or two, look at the image and decide whether to proceed, perhaps do strategy and so on. And then you'll collect the images and we're going to process the images as described in the following slides. A couple of things that are different than years ago. Nowadays at modern beam lines, people try to bring excess crystals. they will often simply collect the images. They won't do a diffraction or image or two. They won't look at the images. They may do different exposure times, different distances, and so on, and hope that they luck out. One thing not mentioned in the lecture that I saw on YouTube is that what people do is sometimes the beam is much smaller than the crystal, and they will raster or do different shots through the crystal, or even collect complete data sets at different places, trying to find the best part of the crystal that has the lowest mosaicity, the least ice, the highest resolution diffraction, and so on. And this is now becoming standard, I think, at synchrotrons. So some of the expectations for data quality are listed here, and most of these are showing up in the table 1 that I described: the completeness, the multiplicity, how many times you've measured individually reflections that have the same intensity, the R factors are measured, are merged, the RPIM, the precision indicating, are merged, the average intensity to the standard uncertainty, or the sigma, or the signal to noise ratio, what's the resolution of the data. Do you have an anomalous signal? Because that's often how the phase problem will be solved. A Wilson plot will give you something, an indication of also resolution, and you'll have to look at radiation damage, which was introducing systematic errors into the data and perhaps detecting twinning. And these things may come from after you have processed the data and you're looking at the data quality. So quickly, things you can do in the experiment: basically at a beamline, everything's set up, there's not much you can do. But you do want to make sure that you're reducing air scatter by putting the beam stop close to the crystal without blocking too many reflections. You want to minimize these air gaps, and you also want to minimize the shadow along the on the images that is caused by this post that comes around, or at least put the shadow in an area that doesn't matter. So here's an example of a catalase crystal from the 2019 crystallography course. This is Thiago. He mounted a catalase crystal, and if you look at this image, you see the spots are kind of swirly. If you zoom in here, which I'm not going to, the spots aren't really well separated, but here's the shadow I was talking about. Would you actually be able to integrate this data and solve the structure? Well, not with this particular setting of the experimental apparatus. This has the beam divergence, the crossfire of the X-ray beam, larger than it should be for such a large unit cell. This unit cell is probably about at least 280 angstrom. But if we change the X-ray source properties physically by adjusting the crossfire of the beam, you can now see that this went from here to here and the spots are separated. So being a very good experimentalist can help you. And it's not just about processing. There is no processing that I know of that would rescue this data and turn it into this data. So be good at your experimental setup, okay? Whoops, an ideal detector is one that counts every diffracted X-ray photon, okay? If you can count every diffracted X-ray photon, then there's nothing more to your experiment, except that, of course, you want to know where the angle the photon traveled from the crystal to the detector, where it came from, and also when the photon hit the detector. So you can get the where from a two-dimensional detector. You have the, let's say, the X value and the Y value, and you can get when by the rotation angle of the crystal, all right? So knowing that, there's really no more information generally available except in deference to polychromatic X-rays. If you know the energy of the photon, that can be useful. But for a perfect experiment, or as perfect as you can get, there'll be no added noise, no zingers, no cosmic rays, no diffraction from, say, ice. I mean, we say every diffracted photon. You're going to measure everything from ice crystals, ice rings, air scatter, and so on. But if you can minimize these photons that are not coming from your crystal and minimize the signal not coming from your crystal, we'll call that background, then that's going to be an ideal experiment. And nowadays you have these Eiger detectors, these Ragaku hybrid pixel detectors, and other detectors that are very close to ideal detectors. This was not the case when I left the field. Okay, you can change your wavelength. That was discussed a little bit, but I only want to say that the wavelength will affect the spot separation, the absorption correction, the radiation damage in your sample, of course, the maximum flux, and I saw a plot of that. You can minimize artifacts of the X-ray source by picking the proper wavelength. And if you're trying to look for an anomalous scattering signal, well, first of all, I'm going to say it until I die, there's always an anomalous scattering, just whether you can measure it or not. You do not have to be at the absorption edge to measure an anomalous scattering signal, and more on that later. The steps are plan everything, and you might look at Tom Terwilliger's paper on CC ANO and S ANO. Once again, initial images, index, collect the data, process the data, do the merging statistics, confirm the space group. So this shows a diagram of the diffraction experiment with some labels and some equations. The X-ray beam is coming in from the left. These red lines are meant to depict Bragg planes in a crystal. This is the center of the crystal, the origin of the crystal. And the evolved sphere has already been introduced. And so you should know that the radius of this evolved sphere is 1 over the wavelength, 1 over lambda. And this is the origin of the reciprocal lattice. And this is a helpful way to visualize Bragg's law, that if you have a incident beam wave vector S0, and I'm drawing it going from the origin of the reciprocal lattice towards the crystal, you can get Bragg diffraction, constructive interference, if the Bragg's law holds. So, which is n lambda equal 2d sine theta, where d is the d spacing and the theta is the angle between this plane that bisects this angle and is perpendicular to this d star vector. There's a theta here and a theta here. So the angle that the scattered beam wave vector S makes with S0 is 2 theta. This is where diffraction ray will continue out and hit your detector and arise at a point xy on the detector. So to introduce this, if we had no beam stop here, the X-ray source would go and hit the detector at what we'll call the origin of the beam. And if we know, say, the X coordinate and the Y coordinate, we can now look at similar triangles here, and we can project this scattered beam wave vector from the point P back onto the surface of the evolved sphere. So this vector from here to P is some scalar times S, S being the scattered beam wave vector. If we get this vector and normalize its length to 1 over lambda, as shown here, we now know what the S vector is. We know from the experimental setup what S0 is. So if we take S0 plus S, we can actually get a value for D star. And D star is equal to these set of 3 by 3 matrices, which I'll describe on the next slide, times the HKL, or the index of the reciprocal lattice point. So once again, S0 comes from, it's a function of the spot position, the rotation value of the image of the crystal when the spot was measured on the detector, and of course the detector position, because we need to know this distance and this distance. So diffraction maths. S0 plus S is equal to D star. D star is generally the reciprocal of the vector D times these 5 quantities. So the three-dimensional vector H is the Miller index. B is the crystal orthogonalization matrix, and it encapsulates the unit cell information. C is the 3x3 orientation matrix of the crystal. And I skipped ahead, sorry. G is the crystal goniometer matrix. So first of all, C is how the crystal is oriented onto the goniometer. G is how the goniometer is, the motors are rotated. R is the rotation of the crystal during the experiment. D is the reciprocal lattice vector, and S naught and S have been described. So it's all linear algebra. Multiply a 3D vector by 3D matrix, 3x3 matrices, and you come out with a vector. So you can look up what the orthogonalization matrix is, but rather than show ABC, because we're measuring things in reciprocal space, it's using A star, the reciprocal lattice vector for the A axis, B star, and of course the angles. The rotation matrix is the crystal rotation orientation matrix, or the crystal rotation matrix, is generally decomposed into 3 rotations around X, Y, and Z. So for an example, X is a rotation around the X axis. And for those of you who know 3x3 matrix, rotation matrix, this should be obvious. As you rotate around X, the X value does not change. So initial images, indexing, collection, and so on. Whether you use the data the images for data collection for imaging or initial images, it's all the same at the beginning. We're going to talk about indexing now. Well, in terms of strategy, this was covered by Jean-Luc in a previous lecture, and I'm just going to say a couple of words here. One is the exposure time will depend on the expected counting statistics and how quickly you want to finish the experiment before radiation damage sets in. Last time he said, well, you collect and then you stop when, well, he didn't say this, but he implied that you kind of stop when you know radiation damage is large. But many people nowadays will collect a full 360 degrees or maybe even 720 degrees because it's so easy. They will then only process the first 180 degrees or the first 300 degrees because they will have processed the whole thing and cut off where the radiation damage is too much. So you have some editing, if you will, of your experiment after the fact when you have more knowledge. So some of the expectations of images is that diffraction is a Poisson process. So what that means, if you have some quantity Q, the variance of Q is equal to Q itself. That means the standard deviation, which is the square root of the variance, is simply the square root of Q. So if we're measuring X-ray photons or X-ray intensity in a spot, and there's no other errors and it's all Poissonian, the sigma is going to be the square root of the intensity. As an example, if the intensity is 100 photons, the square root of that is 10. And so measuring 100 photons, we would know that the standard deviation is 10, or 100 plus or minus 10, or a signal to noise of 10. But integration is not just measuring the intensity. If we look at let's say, we'll call this a one-dimensional experiment, where as we move along in this dimension, the peak enters, or the Bragg reflection, or the reciprocal lattice point now passes from the through the evolved sphere, either from the outside to the inside or from the inside to the outside. You get Bragg, we'll get constructive interference. Bragg's law will hold, and then away we go, and it diminishes as the Bragg's law shows. We get destructive interference when things aren't lined up right. We're interested in this area above background, but we can only measure the background plus the peak. So we must measure the background on either side of this peak in order to estimate what the background is under the peak. And you might do this if you're doing chromatography or something, to look at plots coming out of gas chromatograph or other thing to measure the amount of protein or other signal you have underneath the curve. So doing the same thing here with this one spot, but we might be doing it for tens of spots, thousands of spots, hundreds of thousands of spots, millions of spots, all individually. So in integration here, we would take the sum of everything here, subtract the background. And so because errors propagate quadrature, we know from standard error propagation, we have to take the variance of the peak plus the variance of what we subtracted or added. And that will give us the variance of the intensity, and we take the square root of that. So how does that work? If we look at the relative error, sigma over I, if the background is 0, and I show this, this would be 1 over the square root of I, because the square root of I divided by I is 1 over the square root of I. If we have no X-ray background, this relative error expressed as a percent for 100 photons is 10%, or 1% if we had 10,000 photons. But if we added 500 photons of background underneath here, the signal to noise for weaker reflections increases. So the is reduced. So the signal to noise here is at best, no matter what you can do, is 10 for 100 photons. But if you throw in some X-ray background, the signal to noise could be 3, for instance. Of course, if you have a lot of photons and the background is small relative to these photons, the signal is not degraded. So as an example, if we increase the rocking curve or the amount of time the crystal needs to pass through the Ewald sphere, or the amount of angle, the X-ray background will increase as this curve goes from a narrow peak to a wider peak. If we just have a lot of material and ice in the sample mount, we can actually just increase, or air scatter, we can just increase the background for everything. And this would be a poor experiment. So you want to reduce that background. You want to reduce the noise. So the beam size as small as practical, no bigger than the crystal, small is okay. The crystal mosaicity as small as possible, which means partly the growth, but also partly how well you optimized your cryoprotection and your cryocooling techniques. Make the air gaps as smooth as possible. Use a modern no readout noise detector, and remove something called shutter jitter. You can do that by having a shutterless data collection, which is the modern method. I don't know that for macromolecular crystallography, anything but shutterless is moved. So with the shutter opening and closing, it actually takes time to do this. And there's other things going on. I won't discuss that more. I wanted to throw in a slide here giving a reference for physics experiments, about the validity of those experiments, the reliability and accuracy, because I didn't have time to go into great detail. This is something to read, because in your career, this is part of what we're doing with integration, and how you propagate errors and look at things is important, and how you report them. So two things, accuracy and precision on our data here. Accuracy is do you have the true value, and what is the value of the intensity? So for example, I can measure my height. I'm sitting in a chair right now, so if I measure my height right now, there's a pretty large systematic error because I am not standing up, right? You're not getting my lower legs here, and I know some of you out here watching this are probably laying in bed, and your height's not right if we just measure the top of your head. If you stand up, for those of you who have shoes on, even you may have a systematic error from the heels of your shoes. So accuracy is to get the true value. So we want to know, what is the true value of an intensity? Precision is how reproducible is it? If I measure my height many times, do I get the same value over and over? If I want to know the average height of the people watching this video, you guys would all measure yourselves, report it, and we could do an average of everything. But some of you might say, I'm not going to get up out of my chair, so my height is now I don't know what my height is here. Maybe it's 60 cent. No, it's got to be at least 120 centimeters. So if we look at targets right off of Wikipedia, let's say the true value is at the center of the target. These 4 spots that have hit the target here, they're fairly precise, but they're not the right value. These are all coming in a tight pattern. And the average will be here, but it will be the wrong value. These 4 spots, the average might be closer to the center, closer to the true value, but they won't be very precise. So we're going to always be struggling between accuracy and precision. But you need to know that precision does not trump accuracy. And this was told to me by Michael Blum in 2012. If you measured a Bragg reflection absolutely accurately, you would only need to know that one measurement, and you would be able to solve the phase problem of even the most of, well, not the most, but let's say of many difficult sulfur sad structures, as long as you were accurate. But no amount of precision can make up for inaccuracy. And this is from Charles Whelan's book on statistics. So you must have accuracy first, and it's very helpful to have multiple measurements to get a judgment of the precision, but also to reject outliers, which is the next lecture, not the next slide, the next lecture. So we've collected all this data following best practices, taking the advice of the beamline people of how their instrument works. We've, even before getting to the beamline, we made the best use of our time in crystals by doing cryoprotection and flash cooling without ice and so on. And we're ready to do integration. And all software projects getting reflections from images, or all software packages, will find spots, index, refine, predict where the spots are, integrate them, and they will do the scaling. They may have different names for these things, and I'll show this at the end of my lecture, but they're all needed. So to do the finding of the spots, well, to get we need to know the origin of the beam, or this XY detector may not work. The origin of the beam can be determined from a direct beam position with a direct beam shot. We can look at the center of powder rings or ice rings. There is symmetry here. We can use symmetry to look at this. If you change the detector, the detector, if you change the distance, it may be so heavy that it moves down and the direct beam changes. There's a bunch of experimental things that are important for this. As an example, here's a data set where the red crosshairs is where the software thought the direct beam was. But if you superimpose multiple images, if you overlay multiple images, we expect this red cross to be along this line. It has to be at the center of symmetry and probably halfway between these 2 spots. So before this was moved, the images could not be processed. When it was moved, zoom in here a little bit, it was trivial now to index and process these images. So you must get this stuff correct. All the programs find spots. There are many properties of finding spots. Do you use one image, multiple images? Do you cut off by I over sigma? Do you have a minimum pixel value? How do you exclude spots that are unlikely to be Bragg spots, like the spots in ice rings? You can just exclude those by the known resolution ranges of ice rings. Do you exclude saturated spots or keep them in? If they're saturated, that means you don't know the true signal at the upper end, but you still know the position. Do you use low resolution, high resolution, all, and do you do a filter so that you can filter out cosmic rays or salt diffraction and so on? And something called the Lorentz factor is spots near the spindle have a higher uncertainty in their rotation angle. So all the programs, to my knowledge, allow you to pick one image or multiple images. One images, they're not affected by the wrong spindle orientation. So instead of the spindle rotating this way, it's rotating this way. But from beam lines, everybody knows how the spindles rotate, unless an apparatus got moved from one beam line to another and things changed. But one image is less affected by a crystal that is moving at its location, and it might be moving because you put a pin or base at liquid nitrogen temperature on a magnet that is at room temperature. And now as the heat transfer happens, the thermal expansion coefficient of the pin and mount causes the crystal to slightly move. So one image may be better. You'll have uncertainty at higher spot angle from one image, and maybe you don't have enough spot. With multiple images, it overcomes some things. You can have more spots, but if the crystal's moving or the goniometer is not well described, then you actually have a crystal orientation different among these images, and you'll get a better phi spindle or a phi angle determination. And even with multiple images, do you use 5 images at the beginning, 5 images at the end, or do you do 10 images at the beginning, or you do all the images, and so on? These are decisions that you can change after you've collected the data if you have problems. This shows a cornfield. And indexing is like determining what is the spacing of the rows in this cornfield. So if you look at this, I don't think anybody who's not a farmer can tell you, just looking at this, if there's even rows in this cornfield. But if we change the orientation and look a little bit differently, and actually this is obviously a different farm field, maybe possible, and at a different earlier in the season, we can easily see the spacing between these rows of corn if we look down the right direction. Here is a, well, if we continue the analogy, these is a twin crystal here. We have a lattice over here, and it's kind of bent, and a lattice here. So I just want to show that there is a publication from Ingo Steller, Robert Bolotowski, and Michael Rossman that shows how to do Fourier indexing. And I don't have time to go into detail, but it stems from looking at, let's say, 15 different thousand directions through the crystal and finding 3 non-coplanar directions where things are lined up with the lattice of the crystal. Don't forget that you need to know the detector position, because the S vector is calculated from the detector position, and you're just going to need to do indexing to get within the radius of convergence. But you can get the primitive reduced cell, which is, let's say, the smallest 3D repeating solid that you can use, and you'll fit these to 44 lattice characters. You'll fit these essentially to ultimately the space group. You can have lower symmetry masquerading as higher symmetry, and you're going to figure out the absolute space group later. But just to talk about reduced cells, here are in the green dots here, we can draw a lattice using this rectangle, but we can also draw a lattice using these blue lines, this diamond or this parallelogram or even this larger rectangle. Clearly, the reduced smallest value, as I've shown here, is this guy. And they can be fit to Bravais lattice classes: cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, triclinic. And the software will do this for you. But generally, this is the first time you need to start knowing crystallography as processing data, because you have to pick something that has these new terms for you. If the beam position is wrong, then this scattered beam wave vector, you know, if the beam position was moved over here, you might calculate the S vector wrong, and nothing works. That's the point of that slide. What can be insidious is, here's looking at a precession photograph pattern where the right side and the left side are the same. And you can see the symmetry. And if you look at this line of spots, you can see these two are dark, these two are dark, they match. But if you shift the beam center by exactly 1 lattice row, this now no longer matches this. All the spots are still predicted accurately, but the Miller indices are wrong. And this happens with large long unit cells because the spots are closer together. But even systematic absences can give a clue here. If we look at systematic absences, which I'm not going to go into, but for this crystal, every other spot on this highlighted here by the red box should be present, but only the even ones should be there. And this is in the other direction. So as an example here, this was a 454 angstrom cell axis, and it was misindexed so that this spot was thought to be absent, and this was meant to be strong. But if we do the plots where it's incorrect and where it's correct, we can immediately see that the beam center was off by about a lattice point there. So refinement is to run the equation that I gave you earlier. We can do, by doing a least squares fit, we can take the observed scattered beam wave vector that we measured from our spots, subtract it from the calculated scattered beam wave vector that we know from our Miller index, our unit cell, and our crystal orientation, square it, multiply it by a weight, take the derivative with respect to each of the properties that we're interested in learning, and set that to 0, and we can do a minimization, standard least squares. The crystal mosaicity is not part of that, and it can be problematic because we want to know how much time, how much angle a spot fits through the rocking curve of the experiment. And they're measured different ways. This shows the equation for a rocking curve. And it's problematic because it isn't always a nice Gaussian. Sometimes you have full width at half max is very thin, but the baseline is wide. And various programs treat this differently. The problem with this is if you have a weak reflection next to a strong reflection, the weak reflection will be affected by the tails of this bad plot more so than the strong reflection will be affected. The other example of this is here's the prediction given a mosaicity. This spot was not predicted looking at an image. And if we change the mosaicity to be much, much larger, we start to predict spots that aren't there, which means we may include X-ray background in the intensity. And at some point, it's going to be just right, where you don't overpredict, you don't underpredict, and you measure everything. So integration is we're going to predict where all the reflections are, given our unit cell and crystal orientation and our experimentally known properties of our X-ray diffraction experiment. We can put a box around the reflection. We can assign pixels to the peak and pixels to the background. We can estimate the background values around that peak and subtract it. And so sum the peak, subtract the background. But there's a better way than doing just a simple sum and subtract, and that's doing profile fitting. But before we get to that, this is just showing with a slide from Elspeth Garman at Oxford that in the old days, if you started an image and rotated a degree, you could have a Bragg spot completely fit within one image on the detector or one frame on the detector. Of course, some spots not shown here could be split to varying degrees across the boundaries between images. Like this one is split across the boundaries. But so you can have reflections fully recorded in an image, reflections partially recorded in images, and nowadays almost everything is where you have reflections are partially recorded over many images, and you must sum the values of the integrated photons in each of these images to get the full integrated intensity. I mentioned this already, but this is a slide with color from Bob Sweet, is that if you scan the whole thing and estimate the background on either side, if you have high mosaicity and a large rocking curve, you'll get high background. But here the intensity is let's say concentrated. The mosaicity is small, the background is low, and the standard error propagation rules are here as I described briefly previously. So I over sigma ends up being like this, and it pays to make the reflection sharp. So one wants a bright source, good X-ray optics, and low background. Prediction is running this equation again. We can give an HKL, we can calculate what D star is, or the reciprocal lattice vector, subtract S naught from it, and then do the conversion. Other things that come out of this is we can calculate the mosaicisty, the rocking curve. The Lorentz factor is how fast the spot is passing through the Ewald sphere, and that is a mostly geometric property. Here, given the rotation axis vector, the incident beam wave vector, and the reciprocal lattice vector that is moving by the action of this rotation. The polarization factor is also a geometric factor here, and this comes right out of Wolfgang Kopsch's 1988 paper, I believe. And there are other correction factors. This is all part of integration. You must be able to apply these correction factors as you integrate the data, because these are properties that change depending on how the crystal is oriented on the experimental apparatus and how you do the experiment. And briefly on oblique and incident correction factors is if you have a face of a detector or something detecting your photons, you can have two kinds of materials in the beam, including, and you can have air too, but you can have a window that actually blocks photons or attenuates photons as they go through. So if you come through directly, you'll pass through a shorter distance than at an angle, and this will decrease the counts, or you can have the opposite, where it increases the count. So like if you're in a phosphor or silicon, the more material you pass through, the more chance of interaction you have to convert the photon to a signal in your detector. So these two equations describe those two things. With HKL, you specify the box size ahead of time. You specify a background radius away from the spot between this radius here and out to the edge of the box. Background is calculated. The spot radius is on the inside here, and everything inside here is profile fitted. So here's from an image and a display close up. This would be between this circle and the edge would be the background, but of course you want to exclude the background of the neighboring peaks. So we know from geometry where everything is. So this is not hard to do if you know how to write software. We can exclude those. But with profile fitting, we can do something with the orange part in the center here, that orange part in the center. If we have a spot where the profile, at least drawing a line through one of them, looks like this, and another spot that's stronger, we know from the way we do the experiment that nearby spots should have the same shape and the same intensity distribution within that shape. So here's a weaker spot in yellow. If these are all lined up right, then let's say the value here of this pixel times a scale factor should be equal to the value of the red. And if the shape is the same, and we do this for other pixels in this profile, the scale factor between the red and the black should be the same. So we can sum up all of the pixels and get the least squares fit here of all of these scale factors, okay? But this depends on having the reflections predicted accurately. So if you predict poorly, you'll get a bad reference profile. So as an example, a reference profile is made by summing up nearby non-weak reflections or reflections above a certain signal to noise ratio. And we could imagine that if these were not predicted correctly, we wouldn't line them up right and we would get a terrible profile. And if it's good, they'll be lined up right. So you must be able to predict accurately or your profile fitting will suffer. For box size, you just need to make sure you have enough background pixels around, given the limits of your experiment. There's no reason to make this box here on the right huge, because you'll start including pixels away from the spot and the background will not be measured locally. There's many ways to do backgrounds, and the different software programs do them differently. When integrating, you should mask out the shadows that you know about, and we'll talk about that in the next lecture. Here, the beam stop is not oriented optimally, and what happens here is that reflections that should be here will be integrated. This one is integrated and given a low value of 0, and it might be symmetry related to a pixel reflection over here with a high value. The same thing at masking out the shadow of the beam stop at the center, where spots can be quite strong. And by having a funny shaped beam line or beam stop, you can include erroneous measurements. It's just bad data processing. So some tips for integration here as I wind up the last few slides. Set the detector position so the spots do not overlap. I think I heard Gianluca Santoni tell me that last time or in his video. Set the wavelength so the spots don't overlap. Set this rotation angle increment going from image to image to image so the spots do not overlap. Set the beam divergence, and I gave an example of this, so the spots do not overlap. You want discrete spots as much as you can. If some spots overlap, you're going to get away with it, but not if all spots overlap. And you will certainly have a better and easier time of data processing if, guess what, the spots do not overlap. The other thing is, make sure the crystal is not moving. If it's vibrating because of the cryogenic gas flow or because of other things, such as you left a screw loose, this will make your spots will look fine, but and the images will look good, but the data will not, the statistics of the data will not reflect that. So make sure the crystal does not move, make sure it doesn't move in the loop, make sure the base doesn't move, make sure the pin doesn't move, make sure the magnet doesn't move, make sure the goniometer head is screwed on tight. Make sure the cryostream does not move the crystal. Make sure the beam isn't moving, and the beam lines go to great lengths to temperature stabilize their optics, their mirrors, their monochrometers. You have to do the same thing at home nowadays too. And make sure the beam intensity does not fluctuate, at least over the time range of your individual measurements. So you don't like to have beam flicker and so on. If you are interested in very highly precise thing, you can even put on a test crystal before collecting your real data and check out all of these properties. For example, you can put on a lysozyme crystal to test accurately of what the detector position is and what the roll, pitch, and yaw of the detector. And when things go wrong, well, we'll talk about that more. But I want to jump to an example of XDS. All software must describe the experimental setup, including the properties of the source, the detector, the goniometers, the crystal, and the images. And all software must then find spots, index them to get the unit cell, refine to get these properties better, integrate, and scale. And I actually had XDS input file that I made for 2019. And what it looks like here is if I use this, this is a text editor. And maybe Constantine, you can do a voiceover and tell me that you guys can see this.
Yeah, sure.
Okay, that's all I need to know. Okay, so the way this works is if you read the manual and perhaps if you pick up an example off of the web or something, it may not look exactly like this because I rearranged things in order to match my seminar. The job control is you're going to collect spots, which is finding the spots. You're going to do the indexing and refinement, and you're going to integrate, and you're going to scale. And so these names of these major things in the software are listed here. But the source info includes the X-ray wavelength, the incident beam direction, the way it is polarized, the direction of polarization. The detector info is where it's oriented in space, including the crystal to detector distance and where the beam center hits. The beam center is really this is the beam coming in, the beam center. I like to say the beam doesn't move, but the detector moves around it. And you also need to know how the swing angle of the detector is, if it swings around or swings up. And that's what this detector X and Y axes are. So in the experiment that apparatus I showed for the Cold Spring Harbor lab system with purple in the beginning, the detector 2 theta is not at 0. Okay? And then for those are the properties of the experimental apparatus. And then we look at the parameters for this detector and beamline. This is mostly this detector. It's a Saturn 944 Plus, I believe. The sensor thickness, a few other things. Where the trusted region is or where there's bad regions. And then we have some preliminary information for the properties of the objects that I said you could go in and touch. The crystal info, the rotation axis, the goniometer. Some of these are describing the properties of the images, where you start, they rotate every half a degree, and so on. Where they're located on disk, and now into the controlling of the program to find spots. This is saying we're going to use strong reflections. I think this is 4I over sigma, minimum number of pixels in a spot, or 3. This would help prevent us from finding spots that are only 1 pixel big or 2 pixel big. And for this detector, that's good, but this might not be good for another detector like an Eiger detector. For indexing, we're going to do various things, and for refinement, we're going to refine a bunch of things as well. And so we have finding spots, indexing, and refinement. You can't see my finger pointing to this. Finding spots, indexing, and refinement. And then I'm going to integrate 330 images. And the rest of this has to do with how we do scaling, which I haven't talked about here. But here is a piece of software, not written by me, still following the same outlines that I showed before. Finding spots, although it's called call spots, indexing, and refinement, which is called IDXref, integrate, and scale. And in XDS, it's called correct, I believe. So I'm at the end here. I want to just have a slide introducing the next talk on scaling, because we will be able to integrate everything mostly by what you learned today. But scaling is going to have 4 major things. 4, I guess I put my fingers up here. It's going to determine and confirm the space group. We're going to correct for systematic errors, whatever they are. And I already mentioned in terms of measuring my height, wearing shoes or sitting in a chair are systematic errors. And we have mentioned radiation damage as a systematic error. We're going to validate the standard deviations. Do the observed uncertainties or standard deviations match the expected ones? And we'll talk about that. And finally, we're going to reject outliers. So in summary, get the beam center right, get the detector distance right, find spots, estimate where the backgrounds are, know something about MOSISD. It pays it at least to think or ask about these questions. Experience counts. It's before you do something difficult, why not do something moderately difficult? Like use lysozyme and sulfur sad phasing to test your techniques, your diffractometer, and your processing parameters before you go off and do virus particles or large unit cells and so on. So with that, I will give acknowledgments to many of my colleagues over the years, going back to the early 1980s when these workshops happened, and Ed Westbrook, who helped launch some of my data processing career. Of course, Robert Hoover is not on here, but I started all of this kind of work back before 1985, and many other people have contributed, and Joe Ferrara at Ragaku Americas in particular. So thanks a lot. I will stop there, and I'm happy to entertain questions. I have to say that my chat window did not, well, it disappeared.
No worries, I can read the questions to you.
So if I stop sharing my screen, is that good or bad?
People would be seeing your face, but not your slides anymore.
Okay.
I would recommend it. You could always share it again if you want to show something to answer the question. Okay,
let me do that. I see 6 comments in chat now. And all right, Ferdinand is the same height as me. I like that. And you should take your shoes off, Constantine. Cosmic rays. So cosmic rays, of course, are coming through the Earth, passing through here. What will happen is and to some extent, I think this was shown by Jean-Luc, if you, for example, have a detector, phosphor, or a silicon chip, like on the apparatus or Eiger that he showed, if a cosmic ray goes through there, it will knock electrons around a little bit and put them into their holes or whatever that ultimately get counted. And they will show up on an image as sometimes as a streak if they go through the, let's say they go through the plane of your display. I'm sorry, if they go through the plane of your display, but if they go through perpendicular, they might show up as a spot. And you can see these by superimposing many different images together. And in fact, there's other ways of seeing this, okay? So there are other things. If I took a radioactive piece of glass and held it up to my detector, the alpha particles from that might also be counted on my detector. And you have to be careful about that.
If I may add, there's also a story going around in Germany of people who built their X-ray diffractometer room with sand from the Bavarian forest, which is a well-known, it's where Marie Curie got her zinc blender from. It's full of radioactive material. They had to find, so the urban legend goes, a different building to put a diffractometer in.
That's interesting. I know that certainly for fiber optic tapers in the old day, you used low thorium-containing glass. So thorium is a contaminant of silicon dioxide sand that's used in glass, and that was important. Let's see here. I'm reading here. Once again from Ferdinand, just one practical question. Almost all crystals are measured sitting on plastic loops or something similar. Do the loops affect the beam or reflections at all? Or are they calculated out? So the answer is yes, they affect the scattering of X-rays. All of the materials in the beam will scatter X-rays, but will not, those X-rays scattered do not constructively interfere in the Bragg's law way. So they give rise to counts throughout the whole detector there. And so the more stuff you put in the beam, whether it's air or a big blob of oil used as a cryoprotectant, that will increase the background that you will see around your reflections. And that is not, that, I guess if you have to have something holding your crystal, so you can't get rid of it completely, but if you can, for example, keep it out of the beam, the better off you'll be. Martin, after scaling, do reflections contain absolute or only relative information? As in, can the intensity be correlated to directly to electron density or only relatively after building a model? It's actually only relative, right? You have to put everything on an absolute scale, and the reflection that puts things on an absolute scale is the F000 reflection, which you cannot measure because it's behind the shadow of the beam stop. But what we do know is we do know from previous studies what the electron density is of a carbon atom, in particular, even what an alpha carbon atom is different from a carbonyl carbon atom, different from nitrogen atoms, and so on. And so we can scale our data to the calculated data readily, and that's how that's done. I think that's right. If anybody else wants to say something different, please chime in. Okay, let's see, that's the end of what I see on chat. Any more questions?
Yes, there's one
Junior.
more question.
I see it. Is there any accuracy estimator for data quality? The answer is yes, and that's coming in the next lecture. Well, an accuracy estimator.
He also further asks,
Yeah.
if not, which precision estimator can be seen as the de facto accuracy estimator?
Right. Ana Gonzalez wrote a paper and said that there is quite a bit of difference where you can collect your data and say you do molecular replacement where you find phases from a similar model, a homology model, and a sulfur sad structure where you find your phases from sulfur sad. So if you can collect the data and you need to find the initial sulfur sites or the initial marker atom site or the initial anomalous scattering sites, that if you can find them, that's a good estimator of accuracy of the data quality. And Tom Terwilliger wrote a paper on that. The reality is that those two things are separate things with your data. All of the precision indicating measurements that we'll talk about, or the redundancy, our PIM and our MIM are more telling you something about precision than they are telling you about accuracy. Because if you shifted every reflection, if we put high heels on every reflection and shifted their height, that means they're all inaccurate. And we'll talk about more on this, but one thing that we always use is, can we solve the structure of lysozyme with this minimal amount of data? And after a while, you may get a feel for that. I hope I'm saying this right, but basically the thing is that people will say, well, you know you have accurate data if you've solved the structure, right? You know you have the right data if you solve the structure. So you can still be fooled by some of the statistics that come out of the program. And I'll leave it at that until the next lecture.
Thank you, Jim. I learned a lot, he writes. I also have a remark. So Jim I at least did not gather, he said that looking at diffraction image is increasingly getting out of fashion because measurements happen so fast and are automatic. However, in order to do the best possible experiment, in order to have the highest chance of solving the structure and seeing as much biological detail as possible, looking and understanding your diffraction images is crucial. I get sent a lot of problem cases, and very often the pathology is in the data and the measurement, not in later problems. But perhaps Jim would like to say more about this. I'm sure he's got more experience.
Well, I don't have as much experience as Kai, who was on this talk earlier.
Yes, video
he's
is
still
cool.
here. And maybe he asked that question. It sounds like a question from, but anyway, hello there. So he's turned on his video.
But your microphone is still muted, Kai.
No matter. I'll address the question. It is true that in the old days, you had the leisure and time to look at every images. And so it is possible that, and we saw this in the Cold Spring Harbor course, where people they get synchrotron fever and they want to collect data on anything. And if you look at the first image, somebody who has seen thousands of images know that they are not going to do sulfur SAD phasing from that image just by looking at it. On the other hand, the statistics that come out from scaling are going to help you show that these things they're going to reflect what you can learn by looking at the images. So if you can get a bunch of things right, you actually don't have to look at the images. That doesn't, so if you collect like 50 crystals and then you automatically process them and it says, oh, 45 of these are not any good, but these 5 are good, and you solve the structure, generally you're going to be happy. However, that doesn't mean in the 45 where the statistics were bad, there wasn't something that was better, and it was only bad because the beam center moved for some reason. So you don't have a chance to look at images, but I wrote a program that ranked images without knowing anything about the unit cell. And this DT ranker program, you could say, well, it's like a spam filtering. It's actually modeled after a program called Spam Assassin. You got positive points for good things in the image, discrete spots that were circular and tight, spots that have high I over sigma. You got points subtracted for ice rings, the rings that you see. You could measure the background in different parts of the up here, down here, over here. And it added all of these things up, and it looked at the I over sigma. So as you went to higher resolution, and if the number of strong spots in the outer shell remained decent, you got more points than if they faded away. And this program actually corresponded, the ranking corresponded quite well to the results that came out of this. And more importantly, it was consistent. So if you had a data set of 300 images, where everything was collected right, you could use the first 10 images and get a score, and the last 10 images and get a score, and the scores would be well within the standard uncertainty of doing this, so you could get scores throughout. So there is a way that you can have software look at images and help you. On the other hand, with modern stuff, it's just amazing what you can do. So I'm not sure that you might go and look at images, and you might next week ask the same question, okay? I see, I'm gonna stop there and I'm gonna read Gordon's thing. This is a general question. How do you think X-ray compares with NMR for structure determination? It doesn't seem to me that the resolution is better. They give different kinds of information. I am not an NMR person, but I do know this, that for NMR, structure determination isn't used as much anymore because X-ray has proven itself as being better. There are different kinds of questions that can be answered. Maybe NMR can do things better, but I do know that years ago, Glaxo shut down their NMR group in Research Triangle Park, and all of those scientists came to the Cold Spring Harbor course over many years. So certainly if you ask this question about cryo-EM, I will defer to cryo-EM structures, but they're different, and so they complement each other. I do know that I was involved in the very first comparison of tendamostat, of an NMR structure with an X-ray structure, and the structures were the same. Despite what Kurt Wuthrich said, there are some things you cannot see in the X-ray structure on the surface. If a side chain is moving around, you won't see it in an X-ray structure. And they said, well, they saw it. So I like both methods, but I'm a crystallographer, so I have to say there is a difference. And I'm sorry. There we go. Okay. You're smiling, Dale.
Gordon has written a little bit more. NMR is used for structure determination. My studies of RDCs, for example, indicate no difference in structure or accuracy between NMR and X-ray.
What is RDCs?
Gordon, if you like, you can, by the way, also use your microphone.
Studies of RD, okay, residual. So I don't know what residual dipolar coupling is. And if your studies show no difference or accuracy, I just say publish it, okay?
First,
put it out there.
Yeah, of course it is. But, I just want to point out, thanks for the great talk. I'm learning X-ray. I've always wanted to learn about X-ray, how you guys do this calculation. NMR is quite fundamental to structure determination. Yes. Actually. I mean, from the point of view, it's like a protein expert versus a carbohydrate expert. They're sort of orthogonal to each other, and people don't appreciate both points of view. But as far as I can tell, not just from RDCs, but from NOEs, NOSEs, HSQCs, all sorts of different experiments, I don't really yet see an advantage to X-ray. I'm not belittling it. I mean, I've worked with people who used to think that X-rays always gave better structures.
Oh,
and I'm finding out that, more resolved. I mean, you can't beat 2 angstroms, so.
Okay. So so I have no qualms with.
Okay, no, you're not an NMR person, at all. So yeah.
But I'm not an NMR person, and so there you go. Okay.
Yeah, I'm not an X-ray person, but I'm learning. Thank you.
If I would like to comment a little bit on that. I'm also not an NMR person, but I had to do a little bit with NMR people. Now, a coupling is a relationship between atoms. NMR is fundamentally different in the type of information it provides, as is, by the way, cryo-EM. So it is my opinion that in order to solve one question, you need one. In order to solve the other question, you need the other. NMR is absolutely great if you have any problems with something that is very movable, if you want to know how something behaves in solution, and particularly excels if the structure is not very large, or you can basically blank out some of your coupling. X-ray crystallography can give you a three-dimensional image, but it doesn't tell you so much about the motion. It is the static structure.
Well, actually, no. NMR can give you a conformational information that X-ray cannot, and NMR can also give you interdistance, atomic distance information that, of course, X-ray can too. But conformational changes are extremely important for proteins and also carbohydrates.
Yes, that's exactly what I'm saying.
I've yet to understand how X-ray can be used for that.
So I wanted to make an additional comment. In none of these techniques are you using solely the information that you get from the experiment. So for X-ray crystallography, for absolutely sure, we are using prior information. We know, for example, what the covalent structure of the molecule is. We know what an alanine looks like. We know what a phenylalanine looks like. We know what the bond lengths and bond angles, and we know about torsion angles, and we know all of the past structures that have been done. And in the early days, people weren't paying attention to rotamers and so on. Of course, now it's automatic in terms of validation and so on. And in the early days of NMR, at least in the days that I were involved in, those two techniques were learning about validation as we went along, and people made things get closer to they now match. That's, I think, one reason why structures are more accurate now, is because we have all of this additional information. So macromolecular crystallography is not small molecule crystallography where you know where all the atoms are from a 0.7 angstrom resolution structure determination. We are using all of this external information and the biochemistry to actually make the models that we get from the
I understand. My conversation may get really technical, so I shouldn't continue. I came from the CCRC, and I worked with Prestigard and Woods and other people. So
okay.
Yeah. Thank you.
Anything else?
If there are no further questions, I'll just quickly share my screen. So next week, as you've already heard at the end of the lecture, Jim is going to give us a second part, which will be diffraction, image processing, scaling, and statistics revealed. As you can see from the picture, he's also going to wear a cowboy hat while giving this lecture. And so I'm looking forward to see him and all of you back next week. Have a nice day.
Thanks, everyone.